A network of nodes, a maze, a map, a social graph. Starting from one node, how do you reach every other? There are exactly two ways. One sweeps outward in rings, breadth first. The other dives deep down one path, then backtracks, depth first. Same graph, two very different sweeps. Let me show you both. One quick, honest note before we dig in. Everything in this video is free, no wall, no catch. This exact visual style is the whole idea behind my book. Algorithms and Data Structures, Visually Explained. 23 of them, each a clean diagram and runnable Python. Graph traversal is in there too. $24, link below. Totally optional. Now, let us explore a graph. First, the graph itself. A graph is just nodes connected by edges. Here we have 7 nodes, A through G, joined by edges. A connects to B and C, B connects to D and E, C connects to F, E and F both connect to G. These edges are unweighted, no distances, no costs. An edge just says, these two nodes are neighbors. And they run both ways. We fix one starting node, A, and our goal is to visit every node reachable from it, each one exactly once. The only thing that changes between our two algorithms is the order we visit them. To pull that off, both algorithms keep two things. First, a set of nodes already visited, so we never repeat one. Second, a to-do list of nodes still waiting to be explored. That to-do list is the whole difference. Breadth first uses a queue. Depth first uses a stack. Breadth first search. BFS. It explores in rings, and its to-do list is a queue, first in, first out. Start by putting A in the queue and marking it visited. Then repeat one simple step. Take the node at the front of the queue, visit it, and add all its unvisited neighbors to the back. Pop A. Its neighbors are B and C, add both to the queue. Order so far, A. Pop B, from the front. Its unvisited neighbors are D and E, they go to the back, behind C. Then pop C, and add F. See the ring forming? A was distance 0. B and C are distance 1, everything one edge from the start. Now the queue holds D, E, F, the distance 2 ring. Pop D, its only neighbor is B, already visited, so nothing new. Pop E, it adds G, pop F, G is already queued, skip. Finally pop G, the lone distance 3 node. The full visit order, A, B, C, D, E, F, G, level by level, ring by ring. And here is the payoff, because it fans out evenly, breadth first reaches every node by the fewest possible edges. On an unweighted graph, BFS finds the shortest path. Now depth first search. DFS, same graph, same start, but instead of a queue, it uses a stack. Last in, first out. And that one change flips everything. Instead of fanning out, depth first plunges. It follows one path as deep as it can go before it ever considers a sibling. Start at A. Go to its first neighbor, B. From B, go deep to D, D is a dead end, its only neighbor is back at B. So we backtrack, pop it off the stack, and try B's next neighbor, E. From E we go to G. From G we go to F. From F we reach C. That is as deep as it goes, a single long chain, A, B, E, G, F, C, 6 nodes on the stack. Now everything is visited, so we backtrack all the way out, popping the stack. The visit order, A, B, D, E, G, F, C. Notice, depth first hits G on its very first plunge, while breadth first saved G for last. Same graph. Because the stack is last in, first out, it always dives into the most recent node first. Recursion does the exact same thing, the call stack is the stack. so put them side by side. Same graph, two temperaments. Breadth first spreads in rings. It uses a queue, visits nearest first, and on an unweighted graph it gives you the shortest path, the fewest edges to every node. The cost, it holds the whole frontier in memory. A wide graph means a wide, hungry queue. Depth first plunges. It uses a stack, or plain recursion, and races to the bottom of one path before trying the next. Its memory is only as deep as the current path, which is usually far smaller. But it does not find shortest paths, it finds a path. That difference decides what each is for. Reach for breadth first when distance matters, shortest routes, the fewest degrees of separation between two people, a web crawler fanning out by clicks. Reach for depth first when you just need to go deep. Does a path exist? It powers maze solving, cycle detection, ordering dependencies with a topological sort, and flood-filling connected regions. Same map. One asks how near. The other asks how deep. Here is both, in real, runnable Python. They are almost twins. Breadth first, keep a visited set and a deque. Pop from the left, that is the front of the queue, record the node, then push its unvisited neighbors onto the back. Popping from the left is what makes it first in, first out, and gives you those rings. Depth first is even shorter as recursion. Mark the node visited, record it, then for each unvisited neighbor, call yourself. The function call stack is your stack, last in, first out, for free. Swap a queue for a stack, and rings become a plunge. That single data structure choice is the entire difference between the two. Let us lock it in. A graph is nodes and edges, and traversal means visiting every reachable node once. Breadth first search uses a queue and visits level by level in rings. On an unweighted graph it finds the shortest path, at the cost of holding the whole frontier in memory. Depth first search uses a stack, or recursion, and plunges down one path before backtracking. It uses less memory and answers does a path exist, powering maze solving, cycle detection, and topological sort. For our graph, breadth first visited A, B, C, D, E, F, G, ring by ring. Depth first visited A, B, D, E, G, F, C, deep, then back. Same graph, two orders. The whole idea, queue for rings, stack for plunge. That one swap is breadth first versus depth first. So that is graph traversal. Breadth first fans out in rings with a queue. Depth first dives deep with a stack. Pick by whether you care how near, or how deep. Next in this series, we look at Bloom filters, a tiny structure that answers definitely not, or probably yes, in constant time. It is how databases and browsers skip work they can prove is unnecessary. It is clever, and a little bit magic. If you want the whole picture, 23 algorithms and data structures, each a diagram and clean Python, my book is linked below. $24, totally optional. Subscribe, and I will see you in the next one.